When engineers attempt to apply rigid body mechanics to a substance that cannot maintain a fixed shape, the traditional equations break down. A solid block will resist a tangential force up to its breaking point, and then it fails completely. To model non-rigid materials, we need a strict definition. A fluid is a substance that undergoes continuous deformation when subjected to any applied shear stress, regardless of how small that applied force might be. It does not deflect and hold, it flows. This graphic contrasts the chaotic reality of microscopic fluid particles with the mathematical model we actually use to solve problems. Tracking billions of erratic molecular collisions is impossible. Instead, we use the continuum hypothesis, treating the fluid as a single, uninterrupted macroscopic mass. This assumption holds true only within a specific mathematical boundary. The Knudsen number, the ratio of the molecular mean free path to the physical scale of the system, must be less than 0.01. Below this limit, the gaps between molecules become statistically irrelevant. Once we accept the fluid as a continuous medium, we have to classify its properties to set up our governing equations. In thermodynamics and fluid mechanics, every property falls into one of two strict categories, intensive or extensive. This table categorizes these variables. Intensive properties, like density, pressure, and temperature, are completely independent of the mass of the system. Extensive properties, like total volume or total energy, scale directly with the amount of matter present. By combining the continuum hypothesis with isolated intensive properties, we strip away the unpredictable physical states of individual molecules. This is the required first step to convert a chaotic physical reality into solvable engineering equations. With our boundaries set, we can establish the fundamental metrics needed for hydrostatic analysis. The most familiar is mass density, the exact amount of mass contained within a single unit of volume. If we want to know the physical force gravity exerts on that exact same unit of volume, we calculate the specific weight. Mathematically, it is simply the mass density multiplied by the acceleration due to gravity. In thermodynamic equations, we often need to flip the perspective. Specific volume is the direct mathematical reciprocal of mass density, telling us how much physical space is occupied by a single unit of mass. To compare different fluids quickly across various environments, engineers use specific gravity. This is a dimensionless ratio that divides the density of your working fluid by the density of a universally accepted standard. For calculations involving liquids, that universal standard is water. For gases, the standard reference is air. Looking at the bottom banner of our properties table, we see the critical constants required for baseline engineering exams. Water is pinned at exactly 1,000 kilograms per cubic meter, and mercury carries a specific gravity of 13.6. Specific gravity acts as a mathematical shortcut in hydrostatic analysis. It allows engineers to calculate the pressures of obscure industrial fluids using only the documented properties of water. Hydrostatics assumes fluids are largely incompressible, but real-world high-pressure systems test that assumption. To measure a fluid's resistance to compression, we calculate its bulk modulus of elasticity. This diagram illustrates the mechanical cause and effect. An applied increase in pressure acting on a closed system forces the fluid molecules closer together, resulting in a measurable decrease in total volume. The Step 3 equation defines the bulk modulus, represented by K, as the strict ratio of that compressive stress to the resulting volumetric strain. While bulk modulus measures resistance, the actual property of compressibility is defined as its direct mathematical reciprocal, 1 divided by K. Calculating this modulus depends heavily on thermodynamic boundaries. In an isothermal process, where temperature remains perfectly constant, the bulk modulus is exactly equal to the applied pressure. Conversely, in an adiabatic process, the compression happens so rapidly that no heat can transfer out of the system. Here, the bulk modulus equals the pressure multiplied by the specific heat ratio gamma. These variations in compressibility provide the mathematical basis for predicting destructive pressure waves, such as water hammer phenomena, which can rupture high-pressure hydraulic lines. Deep inside a liquid mass, molecules pull on each other equally in all directions. But at the boundary layer, the lat of upward molecules creates an unbalanced inward tension. This invisible line of cohesive force is surface tension. Because it acts along a boundary line, The standard SI unit for surface tension is expressed as newtons per meter. Looking at this textbook excerpt, we can see how this tension creates a pressure differential. For a solid liquid drop, the internal pressure exceeds the external pressure by exactly 4 times the surface tension divided by the diameter. A SURF bubble is different. Because it is hollow, it possesses both an inner and an outer surface interface. That double boundary doubles the cohesive force, raising the numerator to 8. For the continuous cylindrical geometry of a liquid jet, the surface forces are distributed differently, and the governing numerator drops down to 2. When surface tension interacts with a solid boundary, we get capillarity, the ability of a liquid to pull itself up a narrow tube. The height of this rise is heavily dictated by the contact angle between the liquid and the solid surface. The crucial exam constants to memorize here are the contact angles, assumed to be 0 degrees for perfectly wetting water, and an obtuse 128 degrees for non-wetting mercury, which actually depresses in a tube rather than rising. These microscopic cohesive forces dictate major industrial hardware limits. Together with vapor pressure, surface tension parameters determine exactly when a working fluid will flash into vapor and cause catastrophic cavitation inside industrial pumps. When a fluid moves through a pipe, it doesn't move as a single solid block. At the exact microscopic point where the fluid touches a stationary solid wall, the fluid particles adhere perfectly to the surface. Their velocity is strictly 0. This is the no-slip condition. This chart plots the immediate result of that condition. Because the bottom layer is stuck at 0, the layer above it drags against it, moving just slightly faster. This continuous dragging creates a structured velocity gradient. The friction between these sliding layers generates internal shear stress. Newton's law of viscosity states that this shear stress is directly proportional to the velocity gradient, with the proportionality constant being the fluid's viscosity. This matrix isolates the 2 ways we measure this friction. Dynamic viscosity, represented by μ, is the absolute physical measure of the fluid's internal resistance to flow under an applied force. The standard SI unit is the Pascal second. However, many engineering applications use the older CGS unit, the poise. 1 poise converts exactly to 0.1 Pascal seconds. If we take that dynamic viscosity and divide it by the fluid's density, we get kinematic viscosity, represented by nu. This removes the mass from the equation entirely, representing momentum diffusivity. The CGS unit for kinematic viscosity is the Stokes, which converts to a baseline of 10 to the -4 square meters per second. The distinction is vital. Dynamic viscosity tells an engineer exactly how much raw physical force is required to push a fluid through a pump. Kinematic viscosity dictates how fast the resulting flow characteristics will spread through the piping system. Newton's linear law of viscosity perfectly describes water and air, but in the chemical and petroleum industries, fluids often completely violate this perfectly linear relationship. This graph maps the overarching study of rheology, the behavior of fluids under complex, nonlinear stress. When plotting shear stress against the velocity gradient, we see distinct paths that diverge sharply from the straight Newtonian baseline. The lower curve represents pseudoplastic fluids, which are shear thinning. As the shear rate increases, their apparent viscosity actually drops. Paint and human blood flow this way. They flow easier the harder you push them. The steep upper curve maps dilatant fluids. These are shear thickening. Under extreme stress, their viscosity spikes, causing them to physically lock up and act almost completely like rigid solids. Quicksand is the classic example. Then we have Bingham plastics. Notice how the line doesn't start at 0. These materials act strictly as rigid solids until a specific yield stress threshold is breached, at which exact point they begin to flow just like a liquid. Think of squeezing toothpaste out of a tube. This classification matrix separates all of those behaviors from time-dependent fluids. For these specialized mixtures, the apparent viscosity changes based strictly on how long the shear force is applied, even if the force itself remains constant. Thixotopic fluids undergo a decrease in viscosity over time, like certain printer inks that thin out as the machine runs. Rheopectic fluids do the exact opposite, thickening over time as constant shear is applied, like a gypsum paste hardening as it's mixed. Moving from the baseline continuum hypothesis to evaluating mass properties, and finally navigating the complexities of non-Newtonian rheology provides a complete diagnostic framework. By mapping exactly how a fluid behaves under stress, engineers can conquer any flow analysis, no matter how chaotic the medium.